All right, good morning. Thank you for coming back. So today I'm talking about induced subgraphs and coloring, and it's a topic I touched on yesterday, but today I'm going to do it much more slowly and in much more detail and hopefully get further. All right, so just to remind you, and I will repeat a couple of things that I said yesterday, but it's okay. These lectures are not supposed to be, a lecture course. They're allowed to be dependent. Okay, so as before, I'm talking about graphs. Graphs have vertices and edges, and we're interested in the chromatic number of a graph, which is what's the minimum number of colors you need to color the vertices so that adjacent vertices are adjacent. Adjacent vertices have different colors. And the clique number of a graph, which is the size of the largest set of vertices all pairwise adjacent. And it's clear that the chromatic number is at least the clique number. And today we're interested in this question. What can you say about an inequality in the opposite direction? What can I say about trying to bound the chromatic number as a function of the clique number? And that turns out to be an interesting question. Okay. So here it is again, same question. So first of all, maybe it's just true. Maybe you can prove a theorem that says for every graph, the chromatic number is at most some function of the clique number, and that's false. And there are several constructions that show that that's false. I'm gonna do my favorite one. It's the construction of Chudnovsky. So he constructed an infinite family of graphs, M1, M2, M3, and so on, where each of them has clique number 2. It doesn't have any triangles, but the chromatic number of the kth graph in the family is k. And that tells you that you have fixed clique number, and the chromatic number is arbitrarily large, so there's no hope of getting a function like that. So there's a picture of how to construct Chudnovsky graphs here, but I'm going to explain it because I think it's better if I just do it in real time. So let's see. So this is M2. It has chromatic number, clique number 2, and chromatic number 2. So now let's build M3. So to build M3, you start with a copy of M2. It is. So now we're building M3. So you start with a copy of M2, and now you duplicate vertices. So you put another vertex just like him, and you put another vertex just like him. And what does it mean to be just like him? It means that his neighbors are precisely the same as his. So like that, and like that. And now the last step is you add one more vertex adjacent to all the duplicates, to all the copies. So you get this graph, and if you draw it a little bit in a more standard way, it's this graph. And obviously, omega is 2 and chi is 3. Okay, so just to make sure we get it, let's do one more step. We start with a copy, so now we're building M4. We start with a copy of M3. You duplicate vertices. Right, so he is a friend of him, so his neighbors are exactly the same as his neighbors. And so on. He is a friend of him, so his neighbors are exactly the same as his neighbors. And now you add one more vertex adjacent to all the new ones. Okay? And this is M4, and this graph is this graph. And it's not hard to see that the clique number remains 2, that you don't create any triangles by doing that. It's a little bit harder to see that the chromatic number keeps going up, but not very. So, okay, so that's a construction that tells you, sorry, picked up the wrong thing. That tells you that in general, chi is not bounded by a function of omega. And it actually turns out that you can prove something much stronger. So that's the theorem of Erdős. He proved that there are graphs with arbitrarily large chromatic numbers and no short cycles, right? Chudnovsky constructed graphs with arbitrarily large chromatic numbers and no triangles. Here, in Erdős's theorem, not only do you not have triangles, but you don't have any short cycles, right? You can construct graphs with arbitrarily large chromatic numbers and no cycles of lengths less than 100. Or you can construct graphs with arbitrarily large chromatic numbers and no cycles of length less than 1,000, right? However long you want. And of course, if you don't have a cycle of length less than 1,000, you don't have triangles. So it's still true that the clique number is 2 and the chromatic number is arbitrarily large. And this proof is probabilistic. So, right, Michelski construction is an explicit construction. This is probabilistic. I think there might be an explicit construction by now, but I'm not entirely sure about that. But the way this proof works, so you start with n vertices, and you, with some appropriately chosen probability, you put in edges, right, an edge or not an edge, and you choose a probability in such a way that you don't get a linear size stable set. Now, if you don't have a, so right, you start. So you start with n vertices, and you put edges with probability p. So that you don't get a stable set of size Cn. If you don't have a stable set of size Cn, you cannot color with C colors, right? Or 1 over C colors. Let's make this n over C. Right, if you color your graph with C colors, that means some color class has size n over C, and a color class must be a stable set. So you've arranged that the chromatic number is B. This implies bigger than C. The problem is you haven't killed cycles yet, right? There might still be short cycles. But then you prove a theorem that that you can hit all cycles with not too many vertices, again, probabilistically. So and delete most n to the epsilon vertices to destroy all short cycles. And now that's exactly what you wanted. You have a graph, so maybe you deleted a little bit of vertices, but you still have 99% of the vertices there. And you still don't have a big stable set, so the chromatic number is big. And that's exactly the construction that you wanted. All right, so we'll remember that because I'll keep coming back to this theorem. So let's try to remember it. So, okay, so we convinced ourselves that really there's no chance of getting a function that always works. So then you change the question, you say, when is there a function that works? For what classes of graphs, for each infinite families F, is there a function F sub F so that the chromatic number of G in this family is at most, so for every G in this family, the chromatic number is at most this function of the clique number. And the family, right, it's only interesting if the family you're thinking about is infinite, right? If it's a finite family, you can just say, take the maximum of the chromatic numbers and make F be that constant. Okay, so that's the question we want to think about from now. For which families can you find such an F? And now this is going to be a review. I was going to say repeat, but review is a much better word in this context. A review of what I did yesterday. So question 1, when is there equality, right? When does the identity function work? There are nice situations when it works. Bipolar graphs, complement of bipolar graphs, comparability graphs. But then, as we said yesterday, there's this graph that doesn't work as nicely. And that's when you take some graph on 99 vertices and take disjoint union with a clique of size 100. So then somehow this is not a great question. And if you think about it a little bit more, you can construct sort of not interesting examples of this in such a way also. So what we'll want to do is close undertaking induced subgraphs. Say all these properties I'm going to think about, I want for them to be true for the graph and for all its induced subgraphs. So that's what perfect graphs are. So in the context that we're talking about now, it's a family of graphs as a function that bounds the clique number as a function of the chromatic number. By the way, bounds the chromatic number as a function of the clique number, and this function is the identity function. right? So this is what perfect graphs are from this standpoint. And there's something, as you already know, there's something nice to say about them, because the only minimal graphs that are not perfect are odd cycles and their complements. And you can prove a theorem that says if you don't have as induced subgraphs, any odd cycles of length at least 5 and any complements of odd cycles of length at least 5, then the graph is perfect. And what we want now is similar theorems for other functions. I mean, ideally, I want to say, you know, if you forbid this, this, and that as an induced subgraph, then there is a function, and if you forbid anything else, then there isn't a function. And that's sort of the theorem you would like. And we're nowhere near sort of having any kind of conjectures that might be in this direction. So the kind of results I'll show you is if you forbid this, there's a function. If you forbid that, there's a function. And it's not clear what the dichotomy is. Okay, but so this is a theorem for perfect graphs. And one more thing, as I mentioned yesterday, the proof of the strong perfect graph theorem was by trying to describe all Besch graphs, by trying to describe all graphs that don't contain odd cycles or their complements as induced subgraphs. In general, you know, it would be nice if there was a theorem that in general describes a graph with fixed induced subgraphs forbidden, but there seems to be no hope of that. So in general, the proofs are not like that, not explicit like that. You go ahead and you try to just zoom on an important part of the graph and find a certain induced subgraph there. But I'll do more details of that later. The only thing I'm saying is this is basically a structure theorem. You know, we can sort of complain that it's not a complete construction, but in the world of theorems, this is a theorem about structure. And that was yesterday. The theorems I'll show you today are not like that. They are not theorems about structure, they're theorems about color. Okay, this we don't need. Okay. So let's move on. Just to have some vocabulary so that we can talk. So a class of graphs is chi-bounded if, first of all, I want it to be closed under induced subgraphs. And second of all, I want that there is a function so that the chromatic number is at most this function of the clique number for every graph in the class. And I'm going to call f a chi-bounding function for this graph, for this class. Now, there's another question you can ask is what is the best chi-bounding function? But that's not what I'm thinking about. The functions I'm going to give you are, it's just some function that gives you an upper bound. There's, you know, chances are they're not even close to being best possible. That's a different question you can think about. All right, so then perfect graphs are a chi-bounded class with chi-bounding function identity. And obviously identity is the best you can do. And just another little bit of notation, I'll denote by 4 above h the class of graphs that don't contain h as an induced subgraph. In everything I say, this notation, this containment relation is an induced subgraph. At most containment relation. So 4 above h are graphs that don't contain h as an induced subgraph. Okay, so is it possibly true that 4 above h is chi-bounded for all h? And the answer is no, because take h to be a triangle, right? And that's these graphs. They don't have triangles, and they don't, and it's not a chi-bounded family. So that's completely false. But in fact, you can prove that there are very few h's, you know, if any. There are very few for which 4 above h is chi-bounded, because if 4 above h is chi-bounded, then h has no cycles. And why is that? It's because of this theorem, right? Suppose h has a cycle, then h is a fixed graph. It has 100 vertices. So now let's look at the class of graphs with no cycle of length less than 100. So it doesn't contain h, because to contain h in particular, you need to contain the cycle in h. And yet we know this family already is not chi-bounded. So, okay. So if 4 above h is chi-bounded, then h has no cycles, and what graph, there's a name for graphs without cycles. They're called forests, and if they're connected, they're called trees. And there's a conjecture that actually it's if and only if. For every forest, the conjecture of Jeffers and Sumner says that for every forest, for every graph with no cycles, form of H is chi-bounded. And it's a well-known conjecture, people are thinking about it, but it's hard, it's very hard. And it's one of those things that's so hard you start wondering maybe it's just false. One reason why it's so hard to prove. So there are a couple of known cases, We know it when H is a path, and that's actually Jeffers himself proved it when he made this conjecture in the same paper. And then Kirsten and Penrice proved it for trees of radius 2. So it's a tree of radius 2, it's a tree that has a vertex so that everybody is a distance at most 2 from it. By the way, so I said, keep going back and forth between forests and trees. Every forest is contained in a tree, right? Just take all the components and add one more vertex with a neighbor in each component. So if I wanted to prove this theorem, it's enough to think about trees. So that's why I won't be careful about saying forests. Okay, so Jeffers proved it for a path. Kirsten and Penrice proved it for for trees of radius 2. Then they had a theorem for some trees of radius 3. And then I think Scott and Seymour sort of pushed their ideas further and got a theorem about all trees of radius 3. But it's very hard, and they kept sort of going back and forth on whether we're going to write it down. So I forget now if it's a paper or just a thing they proved. Recently with Alex Scott, Paul Seymour, Sophie Sperkel, we proved that this tree, the conjecture is true for this tree. But it's hard, it's very hard. And there's something here which is nice. So that's a topological version of the conjecture. And what does that mean? So Jeffers' conjecture talks about form of H. I want to think about something that I call form star of H. So what's form star? In form of H, one induced subgraph is excluded. In form star of H, infinitely many induced subgraphs are excluded, but they're precisely the graphs that are obtained from H by subdivision. So subdivision means that you take a graph, here's the graph. Subdivision just means put vertices of degree 2 inside of edges, right? Subdivide edges. So this means every subdivision of H is excluded as an induced subgraph. So somehow subdivisions are a topological concept, but induced subgraphs are a very kind of combinatorial concept. And this is both. Right? This mixes the two up. So that's form star of H. And now Jeffers' conjecture says form of T is chi-bounded for all T. What Scott proved, so conjecture, and what Scott proved is that form star of T is chi-bounded. And so for every tree, if you forbid all its subdivisions as induced subgraphs, you get a chi-bounded class. And if there's time at the end, I'll come back and talk a little bit more about this semi-topological variant of this problems. And it's a very clever proof, but it's not a very long proof. It's like maybe 20 pages long, but every paragraph takes you a day to read. But it's just very clever, but it's not very, very long. Okay. So that's what I wanted to say about the Jeffers-Sumner conjecture. Now something else, still about chi-boundedness, but forgetting Jeffers-Sumner. I mean, the way I presented it today, I said, well, being perfect is a special case of chi-boundedness. But I think the way it evolved really is that first people thought about perfect graphs, and then they said, oh wait, let's relax perfection and think about chi-boundedness instead. So if you go in that direction, then a natural question to ask is, what if I forbid some whole lengths? Right? So for perfection, I forbid all odd whole. I should tell you what a whole is. A whole is an induced cycle of lengths of this form. So it's in the graph, right? It's induced subgraphs at the cycle of lengths of this form. So to be perfect, you need to forbid all wholes of odd lengths, and you need to forbid all their complements. Now, what if I'm not quite so greedy? I'm not asking to be perfect, I'm just asking to be chi-bounded, but I still want to somehow say it in terms of forbidding lengths of holes. What kind of things can you say? What if I forbid all even holes? What if I forbid all holes that are 3 mod 5? What can you say? So that's what I'm going to talk about next, because that's what people think about. So the first observation is that in order to prove a theorem that says, let I be a set of integers, if all holes of length I are forbidden, then the family is chi-bounded, I needs to be infinite, right? Because if I is finite, then again, look at the longest hole in I, and now look at the family of graphs that don't have holes shorter than that. So this is only interesting for, this is only, I say this is only interesting, I should say this is only hard. It's quite interesting, well, anyway, but it's only hard for infinite families of holes. And there are theorems like that. For example, with Luigi Adario, Berry, Frederick Ave, Bruce Reed, and Paul Seymour, we proved that forbidding even holes gives you a chi-bounded family. And right, so odd holes is perfect, even holes not perfect, but chi-bounded. And the proof there is it's still a structural proof. So what you prove is it's a joke. I see, you guys are a step ahead of me. There's a difference between Asia and North America. In North America, I have one piece of chalk and one eraser. Here, wherever I step. Okay, so let's see. So I'm proving that if G is even hole free, then pi of G is at most 2 omega of G minus 2. Right, so it's not perfect, but it's pretty good. The chi-bounding function is linear, which is very rare. And the way you prove it is you prove that in an even hole free graph, there is what we call a bisimplicial vertex. What's a bisimplicial vertex? It's a vertex whose neighborhood is the union of 2 cliques. Right? I'm allowing edges between cliques, but I'm just saying the set of vertices, the vertex set of the neighborhood of this vertex is the union of 2 cliques. So now why does this imply that? Because let's prove it by induction. Let's delete a bisimplicial vertex. Now you can color with this many colors, but I'm sorry, I wrote 2, I should have written 1. Apologies. Color with this many colors, but now how many colors does he see? Well, his neighbors are cliques. So this is only omega minus 1, and this is only omega minus 1. Because when you add him, you don't get a clique of size bigger than omega. So he only sees 2 omega minus 2 colors, and there's a free color for him. Right, so this, having this bisimplicial vertex just allows you to do a simple induction. All right, so that's that theorem. Then a few years later, Bonami, Charby, and Thomas have proved that, so if you forbid holes of length 0 mod 3, but also forbid a triangle, there the chromatic number is bounded. Right? This is a sort of a version of chi-boundedness theorem, because in the chi-boundedness, to prove that something is chi-bounded, you need to prove that the chromatic number is at most a function of the clique number. Here, I know what the clique number is. It's 2. So So then I need to prove that the chromatic number is bounded, and they did. And this is not a structural proof. This is a proof. I'll show you a proof later in the talk, and this proof is sort of in that split. And by the way, I wrote here 10 to the 6. What they prove is some big constant. I don't know exactly how big. But the conjecture is 4. Okay. So then, not then, but also, Anders Jarfish in the mid-1980s made 3 conjectures. He wrote this paper called Some Problems from the World Surrounding Perfect Graphs, which is such a nice name for a paper, especially since perfect graphs were big then. And basically it was a paper about what happens if you forbid some whole lengths. What can you say about chi-boundedness? He made a bunch of conjectures, but there are 3 I want to focus on. So the first conjecture he made is that if you forbid odd holes, the family is chi-bounded. Don't forbid anti-holes, but on the other hand, the conclusion is not perfection, but chi-boundedness. The second theorem was forbid long holes, then the family is chi-bounded. Now, what's long? Well, for every length, there's a different, for every length, I forbid holes longer than that, and I get a chi-bounding function. It depends on the length and what I mean by long, but it's still true. And then the third conjecture is a generalization of the first 2. So here you forbid long odd holes. You allow all even holes, you allow all holes of lengths less than L, but you forbid odd holes of lengths bigger than L, at least then. And again, it's chi-bounded. So, well, so first of all, if you prove this, then you don't need to bother with those 2. But I should say by now they're all theorems. By now they've all been proved recently in the last couple of years. But the way they're approved is first 1, then 2, then 3. But you have to write your papers correctly, because people go, just like on a test, you go in order, also in paper you go in order. And I want to talk about the proofs a little bit. So first of all, the first theorem, that the family of odd holes is chi-bounded. So that was proved by Scott and Sinner in 2014. And again, it's not a structure theorem. It's, the proof of the strong perfect graph theorem, we don't have a structure theorem, but we have some structural description. Their proof, it is not in any way a description of the structure of graphs with no odd hole. It's really a proof that focuses on finding a chromatic, on proving that the chromatic number is bounded. There is a structural conjecture that would imply that. It's a conjecture of Huang and McDermott. They conjecture that in an odd hole free graph, we can partition the vertex set into 2 parts, so that in each part the clique number goes down. And that would imply chi-boundedness, because let's just see that. So let's say I knew their conjecture. And here's an odd hole free graph. And it has clique number omega. And now I'm able to partition the vertex into 2 parts, so that the chromatic number here is omega minus 1. The chromatic number here is omega minus 1 at most. So then what? I can color this inductively by 2 omega minus 1, with 2 omega minus 1 colors. I can color that inductively with 2 omega minus 1 colors. And then I can just use disjoint sets of colors. And that's 2 omega. So this would be nice. And by the way, in the Scott and Sinner proof, the bound is 2 to the 2 omega. So this this would give a much better bound. On the other hand, I don't know if it's true. The Scott Sinner proof is pretty hard. So maybe this is just false. Recently with Vairi Sivaraman, we proved a version of that for bull frequencies. So if you're, this is a nice structural conjecture, but what if you just want to do chi-boundedness? Then here's something else that would work. Let's prove that you can partition the graph into 2 parts, so that here the chromatic number is omega minus 1, and this one is perfect. This would, I'm not telling you that the clique number went down, but I'm telling you it's much nicer than the graph you started with. So then what? The chromatic number here is 2 omega minus 1. The chromatic number here is omega. And again, you get that's a function. So that's what we proved for Wilford graphs. Okay, so now the second conjecture is, so that's Alex Scott, Paul Singer, and me, that if you exclude long holes, then the chromatic number is bounded. Bounded as a function of the clique number. And then the third theorem is the strongest one, we exclude long order holes. And there are similarities between all three proofs, but these two proofs are really quite similar. Okay, so what I want to do now, I want to give you some hint of what all these proofs look like. But on the other hand, of course, I don't actually want to show you a hard proof. So what I'll do is I'll show you. So this is a common strengthening of those two. Instead, I'll show you a proof of a common weakening of those two. I'm going to forbid all long holes, and I'm also going to forbid C5. Right? So that's my next goal, to prove a theorem that says if you forbid all long holes and you forbid C5, then you get a chi-bounded family. And it's actually a theorem of Alex Scott from 1995. But, it already has a lot of ideas that did all these proofs. Okay, but first I want to show you Jaffish's proof that forbidding a path gives you a chi-bounded family. Because this is very basic and it's a great tool. We keep using it all the time. The technique that you use to prove it. So that's what I will do now. I'll prove this theorem to you. If you forbid a path, then you get a chi-bounded family. Okay, so suppose I have a graph and has some fixed omega and very big chi. And in this context, very big means more than t to the omega, t plus 1 or something like that. So then I'm going to construct induced path length t. That's what I need to do in order to prove Jaffish's theorem. And the way these proofs always work, you assume that you know everything you want for smaller clique number. So you know that graphs with no path of length t and clique number omega minus 1 have small chromatic number. Okay? So assume chi of g is small if omega of g is less than omega and null pt. Right, and so small in the same sense that this is very big. Small is much smaller than very big. Okay, so here's what you do. Start with a vertex, look at its neighbors, and look at its components of its non-neighbors. And I want to start with a connected graph. Okay, so here's this vertex. Its neighbors have small chromatic number, right? Because its neighbors have smaller clique number. Then that means its non-neighbors have big chromatic number, because the chromatic number of the whole graph is big. And you can color components independently, so there's some component that has big chromatic number. So let's just focus on that component. Now the graph was connected, so somebody here has a neighbor in this component. Let's look at all its neighbors. This has small chromatic number. So that means what's left there has big chromatic number. So it has a component with big chromatic number. I'll do it again. Somebody here attaches there. Its neighbors have small chromatic number. So that has a component with big chromatic number. And you keep going like this many times, depending on how much smaller small is than very big. But what are you constructing when you keep going like this? So you have this vertex that's adjacent to that, and it doesn't have any forward neighbors. This is adjacent to that, but it doesn't have any further neighbors, and so on and so forth. So you're constructing an induced path. Okay? Now, there's a neater way to say this proof with induction. as you probably can guess. But the problem is it's nice to have this technique. So that's why I'm telling you the kind of less pretty proof, but where you see exactly what you're doing. And so I'm going to call this technique constructing a Jafresh path. So what does it mean? It means in a graph with big chromatic number and small clique number, I can take a vertex and construct an induced path starting at it. And this induced path leads me to a component, to a connected subgraph with large chromatic number. Right, so every time I say construct a Jafresh path, that's what I mean. Start with any vertex. I'll tell you where to start, but you can start anywhere you want. And you can build an induced path, and the last vertex of it attaches a component of large chi, a subgraph of large chi, but the rest of the path doesn't attach there. Right? That's what we do. Okay, so that's the Jafresh path. Okay, so now I can show you the proof of this theorem, as I promised. You look at graphs with no long haul and no C5. This is C5. And then that's a chi-bounded family. Let's see the proof. So there are two concepts you know. The first one is you need to think about the second neighborhood of a vertex. So I know what the neighborhood is. Right? I take a vertex, the vertices that are adjacent to it, I call its neighborhood. The second neighborhood are vertices that are distance to. So they're not adjacent, but they have a common neighbor with V. And it turns out it's in all these theorems, it's an important distinction between graphs where second neighborhoods have small chi compared to omega and graphs that have a vertex with second neighborhood that has big chi compared to omega. Now, at this point, it makes sense to ask, do I mean just the people at distance 2 or the union of the people at distance 1 and 2? Is it a sphere or is it a ball? But the thing is, it doesn't matter, because the neighborhood has small chi, and the neighborhood, the clique number went down. So that has small chi. So it doesn't, even if it's a ball, the place where it's big is the sphere. So for that reason, I'm sure I won't be consistent with this definition. But, so that's one thing I want. I want to think about second neighborhoods of vertices and their chromatic numbers. And then another trick is something that's called layering. So what's a layering? It's you start with a vertex, and you classify everybody else by their distance from this vertex. Right? So neighbors, second neighbors, third neighbors, fourth neighbors, and so on. And you can do that. Now, I claim if your graph had big chi, then there is a layer with big chi. Because why? Well, you can reuse colors on even layers and on odd layers. Right? There are no edges between even layers and odd layers. There are no edges between even layers, and there are no edges between odd layers. So if all layers are small, then you can, and twice small, you can color the graph as twice small. So there is a layer with big chi, and you can forget everything else. We'll always focus on a layer with big chi. In fact, this layer would have a connected component with big chi. Because again, you can color components independently. So we'll always focus on a connected component of this layer with big chi. So that's one place where it's not a structure theorem, right? I'm not thinking about the whole graph. I keep zooming, I keep focusing my attention on a portion of the graph where I can see there is high chromatic number. And that's where I'm going to eventually produce an induced subgraph that I need. Okay, so that's what we'll always have. We'll have a vertex, and we'll go several steps, and then eventually have a component with large chi. Okay, so now I recommend that you don't read what's written on the top, but I'll tell you what it's supposed to say. So remember, we're in the middle of this proof that no C5 and no long haul gives you a chi-bounded family. So what I want to, as the first step, I want to prove that if all chromatic numbers of second neighborhoods are bounded, then, right, so I start with a graph with small omega, large chi, and at this stage I'm assuming that all second neighborhoods had small chi. Then I claim I can produce an odd hole. And what it says there is that you can bound the chromatic number as a function of the maximum chromatic number of a second neighborhood. But that's how you write it. Where you think, as you say, all second neighborhoods are small. Let's get a bound. So here's what you do. Do a layer until you get a layer with a component with large chi. And then everybody here has neighbors up there, right? That's what it means to be in this layer. And now, so this has large chi. Take another vertex there with a neighbor here. This still has large chi. And now I'm going to build a Jarfish path starting here. And let me build it in red. So I'll take this vertex and I'll build a Jarfish path starting at this vertex. So it would look like this. And I'm aiming for a hole of length L. So I'm going to build a path of length L. And then, because it's a Jarfish path, the way it ends, there's a large connected subgraph of this layer with large chi, and this vertex has a neighbor in it, and all the orange ones don't. Okay? So now, this is only L vertex. This is long, but it's only L long. So I can, if I look at the second neighborhoods, and now I want closed second neighborhoods, the balls of all these vertices, that still has small chi. Like this, each of them has second neighborhood of small chi, and there's only L of them, so this still has small chi. And that's in the whole graph. That's not just in this layer, that's in the whole graph. But this has large chi. So there's some vertex in here which is not in this union. So there's some vertex here which is not a second neighbor of anybody in the orange path. So here it is. This is a connected graph, so I can walk from here to there within this piece. This vertex is special. It's not in anybody's second neighborhood. Okay, so now from this vertex I can go back up. That's what it means to be a layer. And then I can connect those somehow in the top. Maybe I go all the way back up, maybe I can shortcut earlier, but it doesn't matter. So now I want to say this is basically a long hole. So it's definitely a long cycle. How can it not be a long hole? If I have a cycle, but it's not a hole, that means there's some edges like this. But let's see where they can be. So from this to that, there are no chords. This is an induced path. From this to that, there are no chords. So think about it for a minute. And you notice that the only place where there could be chords is from him to this area. Now, one more step. Can there be a chord like this? Can there be a chord from him to orange? And the answer is no, because then this vertex is in the second neighborhood of that vertex. You go 1, 2. Right? But it's not. That was a special property of this vertex. So in fact, if he has chords, they're only to here. Well, okay, so shortcut. Go, take his chord, his neighbor closest to orange, and take this. This is induced, and it contains all of the orange, which is long enough. So that's exactly what you wanted. And this is a still shot of that, and that was a movie of that. Okay, so what did we prove? We proved that if all second neighborhoods are small, then you get a long hole. So what does it mean? That means that there's somebody with large second neighborhood, large meaning large chi. And in fact, every time I look at a subgraph with pretty large chi, there's somebody in it with second neighborhood of large chi. So let's finish this proof and then I'll tell you how to generalize it. Remember, now I claim actually in the C5 free case, second neighborhoods don't have large chi. And let's just say that. So take a vertex. Here it's first neighbors, here it's second neighbors. And I claim the chromatic number of this is not very big. So why is that? Well, The chromatic number of this is not very big because it's only f of omega. I'm in the middle of proving some theorem that there's a chi-bounding function f. And I assume I proved it for omega minus 1. So then this has chromatic number, which is only f of omega minus 1. So let's color this. Let's partition this into color classes. Here they are. And now here, let's classify people by where they have parents. And somebody might have parents in several color classes here, so just pick one. Doesn't matter. So now this is also partitioned into f of omega minus 1 parts. And each part has parents in a color class. So now I'm going to prove that each of these parts has small chromatic number. And that would do. In fact, I'm going to prove that each of these parts has clique number, which is less than omega. Because suppose let's say this part has an omega clique. So remember, all of these guys have neighbors up there. But on the other hand, nobody here is adjacent to everybody in this clique because that'd be a clique of size omega plus 1. So what that tells you, look at the guy here with as many neighbors as possible in this clique. He has a non-neighbor. Right? This non-neighbor has a parent upwards. Now, he is not better than him. So he is not adjacent to all of those. He has a non-neighbor here. But now what you got is a C5. Right? Like this. And that's a C5. So each of these has small omega, which means each of these has chi, which is at most f of omega minus 1. And then we prove that the chromatic number of this is at most f of omega minus 1 squared. Okay. So for C5 it just ends happily. All right, so now let me tell you something about how to do it in the more general case. I mean, not in the more general case, but in the harder conjecture, or the general conjecture. So this step was fine. This step, well, okay, depends a little bit on what I'm proving. If I'm trying to prove, right, so there are two conjectures. There's a conjecture that excluding long holes gives you a chi-bounded class, and there's a conjecture that excluding long odd holes gives you a chi-bounded class. And if you're doing just long holes, then this step still works. And you're going to get that. You're going to get that every reduced subgraph with big chi has a vertex with large second neighborhood. If you're doing long odd holes, you need to modify this step a bit because you don't have control over the parity of the length of this hole. It's just long. But you can. And it's actually not incredibly hard. I'm not going to show you details of that. But what you can arrange is that you have a picture. Okay, so let me just say again where I am. Now I'm going to show you not very precisely how to modify the proof I just did to prove that excluding long holes and excluding to prove that excluding long odd holes gives a chi-bounded class. So the first thing you show is that, trying to generalize that argument, you show that you can, you do this layering, and you can always get to the high chi layer, and you can get an edge in this high chi layer, so that he has a parent non-adjacent to him, and he has a parent non-adjacent to him, and there's a large chi component, so that he has a neighbor in it and he doesn't. And you can clean your graph up a little bit more and arrange that if I look at two vertices here, and I try to connect them through the top, all this paths would have the same parity, lengths of the same parity. And so it's this picture. Let me draw something. So you've arranged that you get to your high chi component. And there's an edge here. I'm going to draw it in green because I believe in the paper it's called the green edge. So might as well make it green. And the green edge has the property that there's a high chi portion here where this guy touches and that guy doesn't. And also they have parents upwards that do that. So then what you do is you start from here and you grow a Jaffish path. And you make it long, you make it length L, like last time. And then you play the same game. You have this L plus 4 vertices. This was big, even bigger. This was big, so in it there's a long Jaffish. Sorry, going too fast. So you've grown this Jaffish path. This guy attaches in a large chi subgraph. This has large chi, so I can delete the second neighbors of all the colored vertices, and still there's somebody left. And you can get a path from here to there, like this. And you can take his parent upwards. And then you try to look at this completion and this completion. And I know that both these completions are the same parity. That's also something I managed. So now what? Right, so I have these two cycles, but they're not induced. Where can they not be induced? It's exactly the same as on the other board. He might have neighbors, but only in the white part, because if he had neighbors in the green or the red, this would be a second neighbor of somebody in the green or in the red. So then that's exactly what you wanted. You have this path with that completion, or you have this path, one longer, with the completion of the same parity. So you got two holes, one even, one odd. Okay? You didn't get two holes, one on length k, one on length k plus 1. That's a different question, and it's not answered here, because I don't know that all of these have the same length. I just know they have the same parity of length. Okay, so that's this case. That's the case when second neighborhoods have bounded chi. Now, let's continue. So in the C5 free case, it was very easy to finish because you could show that all second neighborhoods have second neighborhood with small chi. Here, you can show that. It's not necessarily true. But what is true is that, well, why did that not work? Because there's a vertex with large second neighborhood. Now, concentrate on this large second neighborhood. This still has large means has large chi. So there's a vertex in it with large second neighborhood. Now look in there, there's a vertex here with large second neighborhood. And you can do that many times. Now, what about those guys? They're in his second neighborhood and in his second neighborhood and in his second neighborhood. And what you get is, if you do it many but constantly many times, you have a high chi subgraph, and it's in the second neighborhood of many people. So now there are two cases. So let's just do one step of this. Right? Here's a vertex with large second neighborhood, and now I'm getting another vertex in here with large second neighborhood. And it turns out there's a distinction to two important cases. You look at his neighbors upwards, and you ask, so right now this is partitioned into his neighbors and his non-neighbors. And you ask which of these covers a large portion of that. And it turns out it's different. So if this covers a large portion of that, then when I look at these two covers together, what I get is a picture like this. This covers that, and there are no edges here. And that's called independent. If you cannot arrange that, if in order to cover a large portion of that, you have to use this, then, well, so you don't get that anymore. But instead what you do get is that this doesn't cover this portion, but those guys have neighbors there. Now, this last part, it's not clear at all. You need to, there's another trick that I'm not showing you. But you can arrange that. So then what happens is, I made my first picture too big. I need to make it smaller, sorry. So this is the independent case. The second option is what we call the dependent case. And what that means is you have a portion here complete to this that covers that. But we also have a portion here. We also have a portion here that doesn't have any neighbors there, but that covers all of this. That everybody here has a neighbor there. Right, so somehow you can, in this case, some independence happens. In this case, what you can do is walk from here to there secretly from the bottom. Right, you can, and I'll show you in a minute more precisely what I mean, but it's somehow convenient to be able to construct something in just this layer without bothering the bottom. And then that's what you get in the dependent case. So, okay. So now you do this, so this was just 2. Now you do this many times. And when you do this many times, right, so every pair is either independent or dependent, you use Ramsey theorem, and you can either have, so that tells you either you have a large set of pairs all dependent or a large set of pairs all independent. Now when they're all dependent, turns out this is very nice, because basically you can build a lot of stuff without touching the bottom. Just because you have all these secret passages, you can build anything you need, in particular a long odd hole. That's the dependent case. And I'll come back to that in a minute in the next part of my talk. Now let's think about the independent case. What you get in the independent case is a subdivision of KNN. So basically what you would like to do is so now let's think about the case when I have all these covers and they're all independent. What I want to say is take a vertex here and take paths like this. So I mean, maybe I should say what's a KNN. It's just n vertices and n vertices all pairwise adjacent. And what I'm going to build here is the subdivision of KNN. And the way I'm going to build it, those guys will be the tops. And then to get the bottoms, I'll keep pulling out vertices like this. Somebody with paths to the tops. So you need to be a little bit careful because, if I just pull him out, after I pull out one, it's not clear that I can pull out another one without, this needs to be induced. A lot of it needs to be induced. So after I pulled out one, it's not clear that I can do another one, but in fact you can. So you build a KNN that looks like this. Right, where the tops are one side and the bottoms are another side. Now this is, it's n is like maybe 10L or something. Right? L is the length of the hole I'm going for. So after you've done all this pulling out, it's still not too many vertices that you used. So you still have a lot of the bottom left. Now let me draw that. And I know this is a little bit of details, but I'm almost done with the details and I'll do something else. So what you have is a K 2L or something that looks roughly like this. And there's still a large part of the bottom. Now if you think of this subdivision of KNL, you can get a hole in it, right? Just, you can get a cycle. In the KNN, you can get a cycle. Just go like this. And because they're very just subdivided, I can make it induced. The only problem is it's not odd yet. It's long, but maybe it's even. But then what you do is you say, it's a trick we've already seen. Look at the largest clique here. Size omega. Take a vertex here among all the vertices in the bottom. Take one with as many neighbors there as possible. Here it is. It's not adjacent to all of them. So it has a non-neighbor. He has a neighbor in some other cover, because each of those covers the bottom. So this is non-adjacent to that, I can assume, because he is not better than him. But now what is this? This is either a path of length 3 between them, or if they're adjacent, a path of length 1 between them. And that's exactly what allows you to get a node hole. Right? You walk around the KNN, that's an even path, and then you complete it like this. That's all. Like this or like that, it doesn't matter. And that's schematically depicted here. Okay, so that was getting a long odd hole. And what I want to talk about now, and yeah, so I promised I'll come back to this dependent case and show you how wonderful it is. So I want to raise the screen now because I'm just going to use the board. But please remember this picture. Please remember where this came from. Right? It's you keep taking vertices with large stack and neighborhood, and then there's one case where everything is independent and you get a subdivision of KNN, and there's another case when you get secret passages in the second floor. All right, can we? I was told that if I ask, the screen can be raised. Can you raise the screen? And maybe turn off the projector also. All right. So what I want to think about now is form star, or in general subdivisions. So remember I mentioned there's a theorem of Scott. So there's a theorem of Scott that says that if I fix a tree and for every subdivision of T, S of T, S is not on G, then chi of G is at most F that only depends on T of omega of G. And that was a theorem of Scott. I called it a topological version of the Jeffrey-Sumner conjecture. So I want to think a little bit more about excluding subdivisions. Like fix a graph, exclude all its subdivisions. What can you say about chi-boundedness? So I guess it is thinking about Forbestar. So after this success, Scott made a conjecture that for every H, Forbestar of H is chi-bounded. And without star, we saw it can only possibly be true if H is a forest. But with a star, that argument wouldn't work. So it's conceivable. Sorry? Where is S? So there's no S in the conclusion. That's the point. It only depends on T. Right? I mean, what this says, in other words, is that there exists Ft, so that for every G in Forbestar of T, chi of G is at most F sub T of omega of G. Right? The reason S is here is because I needed to say S is not in G, so I needed a name for it here. It's just a matter of writing it. Okay, so Scott made this conjecture. You know. Yes, thank you. Thank you very much. Okay, this is good. Excellent. Thank you. Okay. So he made the conjecture that something like that is true for every H, not just for H as a tree, for H being forest, and you know the counterexample we had with additive construction doesn't work in general. And this was open for a while. He made this conjecture in the mid-1990s, and only maybe 5 years ago it was disproved. And a family of graphs was constructed. So there exists G1, G2, and so on, so that they do not contain subdivisions of this graph. It's a K4, and you subdivide edges. And these graphs are in Forbestar of this. And they have arbitrary large chromatic numbers. So omega of GI is 2. GK and chi of GK is right? So, okay, so then the question became for which H is Forbes star chi-bounded. And this family is somehow very useful because you can, it's an explicit construction. It's sort of like the Michalski construction, only harder. And you can see which graphs are, for which graphs all its subdivisions are there, and for which graphs not all its subdivisions are there. And then you can, it wouldn't help you to prove for this H, Forbes star of H is chi-bounded, but it will allow you to prove for this H, Forbes star of H is not chi-bounded. And turns out when you analyze this family, you get a lot of information. So I need to cheat a little bit. This would be a nice question. This would be the nicest question, but it's too hard. I'm going to change it a bit. I'm going to have Forbes star sub L of H. And what that means, subdivisions of lengths where every H is subdivided at least L times. LG, so that if S is a subdivision of H with every H subdivided at least L times, then S is not an induced subgraph of G. Right? So, I mean, somehow up to now it's all kind of intuitive. It's the next thing to think about. This is the jump, and the reason it's a jump is because this question is too hard. So I apologize for that. But I'm going to tell you things that are true, but for your intuition, you can just ignore this. Then what you learn from it will be false, but in the right direction. Okay, so the question I want to think about now is for which H Forbes star L of H is chi-bounded. And you can, again, you can use this family and you can see for which graphs their long subdivisions appear there. And it turns out that you can rule out most graphs just by looking at this one family. The only graphs that are still left, it's not quite trees, but it's pretty close to trees. So examine J1, J2, and so on. And it turns out that if Forb star L of H is chi-bounded, then you can say a lot of things about H. You can construct H explicitly. I'll give it a name and then I'll tell you what it means. Then H is what we call a forest of chandeliers. You know what a chandelier is? It's like a fancy lamp. Okay, what's a forest of chandelier? Chandeliers. First of all, let me tell you what a chandelier is. Start with a tree. And now you add another vertex adjacent precisely to the leaves. And if you have some imagination, this is a chandelier. So now you're allowed to take disjoint union of those. And you're also allowed to attach them on one vertex. But you have to use this vertex in at least one. Right? So I've built something so far. And now I'm allowed to bring another chandelier. And it has this important vertex. And I'm allowed to identify this vertex with some vertex there. So some construction. That's a forest of chandeliers. Okay, so it's a theorem. If this is chi-bounded, then H is a forest of chandeliers. And that's a theorem. That's not my theorem. That's a theorem of other people. And it's 4 people, but I only remember two names, so I better not tell you anything. Okay, so now you might conjecture maybe that's all. And I'll phrase it as a question. Is this if and only if? So we don't know that, but we know it in a special case. So there's something called string graphs. What are string graphs? They're intersection graphs of strings in a plane. There are strings in a plane, and these are the vertices, and then two vertices are adjacent if two strings intersect. And all those graphs, G1, G2, and so on, they turned out to be string graphs. So then, with Paul Seymour and Alex Scott, we can prove that this is if and only for string graphs. Right? So somehow this family came from the chandeliers came from that family, and turns out in string graph it's if and only if. Theorem. If G is in Forbes star, so let H be forest of chandeliers. And there is a function f of h, so that if you have a graph G which is in, I guess it's f of h and L, which is in Forbes star H sub L, but also it's a string graph. Then the chromatic number of G is bounded. It's the kind of theorem we want, but only for string graphs. And we prove basically the tools I told you about earlier almost do the proof. Because what you do is, so it's not hard to prove that in string graphs you always get large second neighborhoods. If you don't, then somehow everything goes away easily. So now you do this business. You keep pulling out second neighborhoods. And as before, maybe you have the dependent case and maybe you have the independent case. In the dependent case, I told you can construct a lot of stuff just in this layer without using the base. And in particular, you can construct any forest of chandeliers. Now, so this gives you a forest of chandeliers. Now what about the independent case? Well, in the independent case, you can construct a subdivision of K and N. But we're in a string graph. So, in particular, it's not in particular, you can prove quite easily that the string graph cannot contain K5 as a minor. So, write something. I said too many things, it's time to write them. Proving that G is in Forb L star H intersect string. And first of all, we can prove large second neighborhoods. So then you can take iterated colors. So that means you have this picture. And either they're all pairwise dependent or they're all pairwise independent. If they're all dependent, you could just construct a forest of chandeliers. So they're independent. then you can construct a subdivision of K and N. But then you also notice that in a string graph, has no K5 minor. And the way I mean, not sure the proof, but it has to do with the fact that planar graphs don't have K5 minors. Basically, you draw the strings on the plane, and you notice if you contract something, you'll get a planar graph embedded in the plane. So, okay, so on one hand I got this, on the other hand I got that. But if you look at K66, right? So what's a K5 minor? It's just 5 connected subgraphs, all pairwise with edges between them. That's what a K5 minor is. But if you look at K66, and you call those 1, and then let's see if I can remember how to do this. 1, 2, 3, 4, 5, 6. Okay, let's look at K55. Look at K55, and you call this 1, this 2, this 3, this 4, this 5, and each of them is a connected subgraph. And between every 2, there's an edge. So that's a contradiction. You cannot have a subdivision of K and N in a string graph. And that's how you finish. Let me stop here.